Hello, it seems the camera is working now. My name is Uwe Burghaus. I'm a faculty member here in the chemistry department. Just moved into a new building, Sugihara Hall. I'm one of the 4 physical chemists we have. You can see the door sign here, so I'm specialized on surface science. It's a sub-area of physical chemistry. So we're looking at properties of surfaces, chemical processes on surfaces. So I'm just walking through my lab here, starting one side, one end of it. So what you can see here on the left is one of the vacuum chambers. We run our experiments at very low pressure for keeping the samples clean, we study, and most of our analytic tools wouldn't really work on air. That's why we pump down these systems in 10⁻⁹, 10⁻⁻10 torr range. And perhaps you can see here on the table, that is one of the little gizmos we use. That is a source that generates atomic hydrogen, which we use mostly for cleaning purposes of our samples. So that thing here, vacuum system, is an XPS system, so it's an X-ray photoelectron spectroscopy, and it has a little interlock system here, so we can get the sample in and out of the system without actually breaking the vacuum. And then we can analyze it. So photoelectron spectroscopy, if you remember your quantum mechanics class, that is usually discussed early on in the quantum mechanics class. The technique was actually the beginning of the development of quantum mechanics. Today it's used as a spectroscopic tool. So it gives us information about the chemical composition of samples, also to some extent about the morphology. Now we have 3 of these vacuum systems. That's another one that is half taken apart at the moment. That one we use for kinetics experiments, and that's perhaps also something you remember from a PChem class, even from high school. So we're looking at reaction rates when studying surface reactions. So also that is a vacuum chamber. That is wrapped in aluminum foil for cleaning the chamber by itself. There are some heating belts around, you can maybe see some of them. So we increase the temperature of the entire system to drop down the pressure even more. And pretty typical is the electronic rods here to control the experiments and the spectrometers. So that's our kinetic system. It has a mass spectrometer, and it has an OG system, which is another spectroscopic technique. And can walk to the last one here. It's a fairly large system, consists of 2 chambers, and that's a molecular beam scattering system. It's similar to a laser, but instead of a light beam, we're generating a particle beam. So noise in the background is generated from the pumps we need to drop down the pressure. Also that thing here, that system has an X-ray spectrometer, XPS system, and it has some mass spectrometers, gas dosing, and metal evaporation systems. And that part here is actually generating the beam. These are 3 connected chambers, and we have an adiabatic gas expansion. Adiabatic means that the gas is cooling down. You might remember that from a PChem class. And that way we can generate a quasi-monochromatic beam of particles. And we look then at the scattering of CO or CO2 or something like that on the surface of the catalyst. So we are characterizing catalytic processes on surfaces which are mounted in the vacuum chamber. We can walk around here, but we're pretty much at the end of our system. A little bit of workbench here. So we try to drop down the pressure actually by putting the pumps in that box here. You can see that it's dropping somewhat the noise level in the lab. So you can see the back side with the pumps, and there is a doser also mounted directly in front of us, a metal doser, to evaporate some nano-sized metal clusters on the samples. That's how an industrial catalyst usually looks like. It has a substrate and metal particles embedded on the substrate. So you can see again how the lab looks like. And I think that's perhaps good enough to give you kind of an impression how the system looks like. One of my students will talk a little bit more about what his thesis project actually is.